Hey guys, this is Mrs. Lyons, and I am going to, in this video, work through your homework on double replacement reactions. So if you look up at the top, here's our generic formula for a double replacement reaction. We have a compound AB reacting with another compound CD, and the B and the D switch places, okay? So we end up with AD plus CB. Now, the key thing to think about here is the A and the C remain the first elements in our compounds. The A and the C are the metals, and those have to be the first one listed in our compound. Okay, and remember that a double replacement reaction, when we make our products are going to either be aqueous or solid. Okay, if we have at least one solid formed, the reaction takes place. It happens. If we have two aqueous compounds, okay, as our products, we end up we have no reaction. Okay, so let's look at how these reactions work. Okay, you will need your solubility chart and you will need a periodic table. Okay, your solubility rules. All right, we have to look at soluble compounds versus insoluble compounds. Soluble compounds are what we call aqueous. That means that they're dissolved in water. So all of the compounds in this list will be aqueous. All of our group 1 metals, ammonium nitrate, chlorate, perchlorate, acetates. Those, if a compound contains those polyatomic ions, it will be aqueous, dissolved in water. Our halogens, chlorine, bromine, iodine, are soluble except these few compounds. Sulfates also are soluble except a few compounds. And then we get down here to our list of insoluble compounds. Okay, those compounds, when we come across them, when they're formed as products, we would put an S as their state of matter. They're solid. And as we'll see, as you'll see in the lab, what happens is a precipitate is formed. Okay, so carbonates, phosphates, oxalates, chromates, sulfides, oxides, hydroxides, unless they have a group 1 metal or ammonium. Okay, so all of these are insoluble except this handful. Okay, so let's look at how we should answer these questions, how we should go about it. Okay, so the first thing I'm going to have you do is write a word equation. Okay, so like we said, two things are switching places. The second part of each compound. Okay, so what's going to happen is iodide and nitrate are going to switch. So our compound is going to be aluminum nitrate plus lead 2 iodide. Okay, now once we've got these words, why don't we take a look at our solubility chart and see if this reaction happens. So here we have aluminum nitrate. We know that all nitrates are soluble. So this is going to be aqueous. And then we have lead iodide. So in my solubility chart, here's iodide. And sure enough, lead iodide is insoluble. So what that means is that when we write our equation, we'll show that as a solid. Okay, so now we need to look at these compounds. All right, and we have to write formulas for them. All of these compounds are going to require us to look at the charges on the periodic table and crisscross to get the subscripts. Okay, so aluminum is +3, iodine -1. So aluminum's +3, iodine's -1. Lead, this tells us lead is +2. Nitrate, remember nitrate on our list of polyatomic ions is NO3 with a -1 charge. I'm going to write this up here, NO3 -1. All right. Then we've got aluminum nitrate. Aluminum's +3, nitrate's -1. Lead is still +2. Iodide is -1. Okay, so by writing my charges up there, what I'm trying to do is to only write these formulas once, because I know now that aluminum, the formula is Al, and the charge on iodine becomes a subscript for aluminum, and then iodide is I, and the charge here becomes the subscript. So we've got Ali3. These are our reactants are always going to be aqueous. Okay. Here we have lead 2, so lead, and then nitrate. So nitrate is -1, lead is +2. Okay, so PbNO3, 2, aqueous. And then we end up with aluminum nitrate. So that's going to be aluminum nitrate, NO3, 3. Okay, so the thing you've got to remember with these are we are always going to look at those charges and we're always going to crisscross them. Okay, and then we've got lead iodide. So we've got PbI2. Now, remember this compound was aqueous. This compound is a solid. Okay, so this reaction happens. It takes place. We do need to balance this. All right. So hopefully you're getting better at this. If you look right here, here's a big clue. We've got 3 iodine and we've got 2 iodine. What that means is we've got to come up with a common multiple of 6. So 2 times 3 is 6. 3 times 2 is 6. Now, if I have 3 lead, I need a 3 here. I have 2 aluminum. I need a 2 here for a balanced equation. Okay. All right. Next equation, we have silver nitrate and potassium phosphate. So nitrate and phosphate are going to switch places. Nitrate is NO3 -1. Phosphate is PO4 -3 when we get to it. So I'm going to end up with compounds silver phosphate plus potassium nitrate. Okay, let's look at our solubility table. Because if the reaction doesn't happen, we don't have to write the products. We don't have to write the chemical equations. So let's see, phosphate. Okay, so all phosphates are insoluble. So phosphate's going to be a solid. And then nitrate, potassium nitrate is always soluble. So this one is going to be aqueous. So that means we do need to write our chemical formulas. Okay, remember silver is always +1. Potassium is +1. We said phosphate's -3. So silver's +1, phosphate's -3, potassium's +1, nitrate's -1. And my camera just went away. What the heck? Hold on. Oh, there we go. I don't know what just happened. My computer screen just went completely white. Hopefully I can delete this part when I edit. All right. So we have silver nitrate. So silver is Ag. These are both 1. So we have AgNO3, aqueous. And then we have potassium. The charge on phosphate is 3. So K3PO4. All right. And then we end up with silver, Ag3PO4, and that is a solid. And then we end up, our last product is potassium, KNO3 nitrate aqueous. All right, so let's see. I have 3 silver here and only 1 here, so this needs a 3. I have 3 potassium, so I need 3 here. Let's see, so now I've got 3 nitrates, 1 phosphate, 1 phosphate. So my equation's balanced. All right, let's look at this next one. We have copper bromide and aluminum chloride. So the bromine and the chlorine are going to switch places, which will give me copper 2 chloride plus aluminum bromide. Okay, let's check our solubility table. Let's see, what do we see about chlorides and bromides? They're soluble except if there was silver, mercury, or lead. So let's see, copper chloride is not. So those are both going to be aqueous. So what we can do is write NR, no reaction. Okay? All right. Now let's go to the next one. Calcium nitrate and sodium carbonate. So I'm going to circle the things that are going to switch places. I'm going to end up with calcium carbonate plus sodium nitrate. Now, something hopefully you'll start to recognize, you'll see nitrate a whole lot of times in these reactions. And nitrates are always going to be aqueous, okay, according to our solubility rules. And then calcium carbonate. So let's look here. Carbonates are always insoluble except group 1 metals or ammonium. Let's see, what do we have with carbonate? We have calcium. So calcium carbonate is going to be a solid. Okay, so that reaction is going to happen. All right, so we need to look at our periodic table. Calcium has a +2 charge. Nitrate is NO3 -1. Sodium has a +1 charge. And carbonate is CO3 -2. So then our products, we've got calcium +2, carbonate -2, sodium +1, nitrate -1. All right, so let's write our formulas. So we remember we put those charges there so we know that we're going to crisscross them. Okay, so calcium, so Ca NO3 2 aqueous plus I made a mistake. Did anybody catch that? This should be carbonate as a -2 charge. That would have messed things up. So Na2CO3 aqueous. And you may be saying, wait, why is carbonate aqueous here? It just said it was always insoluble. So that's a good time for us to look at this rule. Carbonates are insoluble except group 1 or ammonium. So see, since sodium is a group 1 metal, that makes this carbonate aqueous. Okay. All right, then we get calcium carbonate. Those 2's are going to cancel out, and we'll just have CaCO3. That's our solid. And then we have sodium nitrate, NaNO3 aqueous. All right, let's look at balancing this one. So I've got 2 sodium on this side and only 1 sodium over there. So I'm going to put a 2 here. Oh, wow. Check it out. That one, that's all I need to do to balance it. So that one is done. Very nice. All right. Moving on to number 5. We have barium chloride and silver nitrate. So the chloride and the nitrate are going to switch places. So I'm going to end up with barium nitrate. And remember, nitrates are always soluble, so that's going to be aqueous. And then we're going to end up with silver chloride. So what do we know about silver or chlorine? If we look at our solubility rules, chlorine is soluble except when it's reacted with silver. So our silver chloride is going to be our solid in this case. All right. If you look at your periodic table, barium is +2, chlorine is -1, sodium is +1. So we end up with a +2 charge on barium, -1 on chlorine. Silver's always +1, nitrate's -1. All right, so we end up with BaCl2 plus AgNO3 aqueous. Both of those are aqueous. Our reactants are always going to be aqueous, okay? And then one of our products is barium nitrate. So barium's +2, nitrate's -1, silver's +1, chloride's -1. So we end up with BaNO3 2 aqueous plus AgCl solid. All right. Let's see. Does this one need to be balanced? Let's see. Is this so? We've got 2 chlorine here and only 1 over here. So I need a 2 in front of the silver. Then I've got 2 silver, so I need a 2 here. And that gives me 2 nitrates, so that equation is balanced. All right? Okay. Number 6. We've got calcium nitrate and sodium chloride. So these two things are going to switch. Now, if you get really comfortable with your solubility rules, you could look at this and see that nitrates are always soluble. Okay, so whatever this is in, it's always going to be aqueous. And chlorine is always soluble except with silver, mercury, or lead. And we don't have silver, mercury, and lead in this equation. So I'm just going to write this right here, Nr. And if you can do that, that's perfectly fine. You don't have to write it out. But just for those of us who are still kind of getting the hang of this, I want to take a minute and I do want to just write it out in words so that you can kind of see. I don't want to jump ahead. So we would end up with calcium chloride plus sodium nitrate. Okay, so now you can see we know that nitrates are always going to be aqueous, and then chlorine is aqueous unless it's with silver, mercury, or lead. In this case, it's with calcium, so that's going to be aqueous also, which allows us to say no reaction. We don't have to write the chemical equation for it. All right. Number 7, iron chloride and lithium sulfide. And again, if you want to start looking at this, if you can get your head around that, sulfides are always insoluble. So I'm going to write this out because it looks like I'm probably going to have something that is insoluble. So my chloride and my sulfide are going to switch places. That's going to give me iron 2 sulfide plus lithium chloride. Okay, now we need to look, and sure enough, there you go, you have a sulfide, okay, and it's not a group 1 metal, it's not ammonium, so this sulfide is going to be a solid. And then lithium chloride, lithium is a group 1 metal, chlorine is always soluble, so this is going to be our aqueous compound. Okay, now iron, the 2 tells us it's got a +2 charge. If we look at chlorine on our periodic table, it's in group 17, so it has a -1. Lithium, we've got lithium and sulfide. Lithium is in group 1, so it's got a +1 charge. Sulfide is in group 16, so it would have a -2 charge. So +1, -2. All right. So we would have iron 2 chloride, so that's going to be FeCl2 aqueous, plus Li2S aqueous, produces irons +2, sulfides -2, irons plus, or lithium's +1, chlorides -1. So we would have and that is our solid, plus LiCl, and that's aqueous. All right, and a quick 2 right here, and our equation is balanced. All right, I have to pause a minute, and I will be right back, maybe. Maybe not. There we go. All right, 3 more. So we have sodium hydroxide and barium chloride. So we are going to switch hydroxide and chloride. And just a peek at our solubility chart tells us that hydroxides are insoluble. So what that means is we are going to form a solid precipitate, most likely. So let's look. We are going to then have sodium chloride plus barium hydroxide. Okay, and if we look at our products, chlorine is always soluble unless it's with one of those 3, and it's with sodium, so this is going to be aqueous. And hydroxide, barium hydroxide, hydroxides are always insoluble. So barium hydroxide is going to be insoluble. Now, if we look for our charges, sodium is +1. Hydroxides, one we don't see very often, but it's OH with a -1 charge. Barium is +2, chlorine is -1. Sodium's +1, chlorine's -1, barium's +2, hydroxide is OH -1. All right, so let's write these formulas. So sodium hydroxide is just going to be NaOH, AQ, aqueous. Barium chloride is going to be BaCl2, aqueous. And then our products are going to be NaCl, aqueous, plus barium Ba hydroxide OH2, and that is our solid. All right, let's look at this. Is this one balanced? I've got 2 chlorine on the reactant side, and on the right side, the products, I only have 1, so I need a 2 here. That 2 in front of sodium means I need a 2 here. So let's look. I've got 2 sodium, 2 sodium, 2 hydroxide, 2 hydroxide, 1 barium, and 2 chlorine. All right, so we are balanced. 2 more. Sodium sulfate and lithium carbonate. All right, so let's look at this. Now, sulfates and carbonates. Let's see. So this says sulfates are soluble except calcium, strontium, barium, and lead. We don't have calcium, strontium, barium, or lead. And carbonates are always insoluble except when they're with group 1 or ammonium. So let's see. Notice something. Lithium is a group 1 metal. Sodium is a group 1 metal. Okay, there's a clue. Group 1 metals are always aqueous. All right, which means that no matter how we rearrange this, our metals are group 1. So this is a NR, no reaction. All right, 1 more. We have calcium bromide and potassium hydroxide. I'm thinking that this is going to be a reaction because that hydroxide, let's look. Hydroxides are always insoluble unless with group 1. Looks like you couldn't see that. Hydroxides only soluble if they're with group 1. All right, so we're going to switch our stuff around. We're going to switch our polyatomic ions. We're going to have calcium hydroxide plus potassium bromide. All right. Let's look at our solubility rules. We said that hydroxide, that hydroxide is going to be our solid. So this is going to be solid. Since this is a group 1 metal, this is aqueous. Calcium has a +2 charge. Bromide a -1. Potassium a +1. Hydroxide is a polyatomic ion with a -1 charge. Calcium is +2, hydroxide is -1, potassium is +1, bromine's -1. All right, so let's crisscross charges and see what our formulas are. We end up with CaBr2. Remember, our reactants are always aqueous. And potassium KOH, aqueous. All right. And then we have calcium hydroxide, so CaOH2, and this is our solid, and KBr, and that is aqueous. All right, is this thing balanced? Let's see. No, because here we have 2 bromine. Over here I only have 1, so I need a 2 here. And that tells me I need a 2 in front of potassium. So let's count. I've got 1 calcium, 2 bromine, 2 bromine, 2 potassium, and 2 hydroxide. So that equation is balanced. All right, guys, so that is just a quick walkthrough of double replacement reactions, how to know if they happen, how to predict the products, and then a little bit of balancing. All right, I hope that was helpful, and I will see you in class.